Heat and temperature. These are two terms that many people often think mean the same thing, but they actually don't. And it is important as a physicist that you have their definitions correct. What is the difference? Let's look at these two items on the screen. On the left is a cup of coffee, and on the right is a lit match. It should be pretty obvious really that the match is much hotter or at a higher temperature than the cup of coffee. But it's not so obvious that the cup of coffee actually contains much more heat. Let's think deeper by looking at the particles inside. In the coffee, there are millions of particles all moving fairly slowly, but heat is a measure of the total energy in a system. So if we add up all the energy of each particle, we find there's loads of heat energy in there. Now, if you look at the match, you see there's only a handful of particles, and although they are zipping around really quickly, because there are few of them, if we add up all the total energy, we find out that there's much lower than in the coffee. Temperature, however, is a measure of the average energy in a system, and as we can see in the match, the particles are moving much faster than in the coffee, so the average energy and hence the temperature is much higher. So heat is the total energy in a system, and because it is energy, it is measured in the same units of energy, joules. Temperature, however, is the average energy in a system, and there's lots of different units for temperature, such as Celsius, Fahrenheit, and Kelvin. Heat transfer will only occur when there is thermal gradient, and by that we simply mean that one region is hotter than the other, and the heat will flow from the hotter region to the cooler one and never the other way around. It should be really obvious to see that. And this heat flow will continue until the two regions have equal amount of heat and they are said to be in thermal equilibrium. At this point, there is no net heat transfer. Heat can travel through a medium and also through space. The medium of heat transfer could be a solid, a liquid, or a gas. The nature and arrangement of the particles in that medium determines its ability and the mode of transferring heat. So it's really important as a physicist that we are able to explain the states of matter in terms of their particles arrangement. So on the screen we have a solid, that's a metal rod, a liquid, and a gas which is inside the balloon. So let's see how the particles are arranged in each one of them. First, in solids. As we can see, the particles are really close together in an ordered structure, and also they are only vibrating. And this is because the particles do not have enough energy to overcome the bonds holding them together. Now let's look at the liquids. And as we can see, they are still close together, they are all touching, but they have only enough energy just to slip on top of one another and move about partially, overcoming those bonds. There is also no order here whatsoever when the particles are all constantly shifting and moving about. Finally, in gases. Now the particles have enough energy to overcome those bonds and they are moving around all over. Again, there is no order here and the particles are all free and separate to move around. So, all you need to know is that particles in a solid are all touching and are in an ordered fashion. In a liquid, the particles are still touching but are in a random fashion, and there are occasional pockets where they can slip on one another. And in gases, they are in a random fashion. It should also be easy to see that the gases take up much more space than liquids, which again take up much more space than solids. So back to heat transfer, and depending on the medium or lack of it, there are three modes of heat transfer. This is conduction, convection, and radiation. Conduction. So here we have two guys holding pieces of rods with one end on the fire. One of them has chosen a metal rod and the other has chosen a glass rod. Which one of them do you think will burn their hand first? It's pretty obvious that it is the guy holding the metal rod. But why so? Well, that is because metals are much better at conducting than glass. Glass still does conduct, yes, just not as well. The transfer of heat via solids is called conduction. But how does heat really flow in solids? Let's zoom in first on the glass rod. Glass is a typical solid, and thus it is made up of tiny particles. The particles near the fire start to gain heat from it. They start to vibrate much more vigorously. Then they collide with the adjacent particles, passing on the energy, and slowly down the way, particles gain energy, vibrating more and more and passing on the energy through collisions. This is how conduction happens in glass and most normal solids, and this is why solids are good at conducting, because the particles in the solids are close together and collide very often. So you can imagine with the liquids or gases where the particles are far apart, they can still conduct, they can still collide, it just won't happen so often. What about the metal? Why is it such an excellent conductor? If you look at the metal, there's still same process happening as in glass. The particles or atoms near the fire gaining heat energy, vibrating and colliding with adjacent particles. But something else is happening. There are these tiny electrons whizzing around. They are called free delocalized electrons. They can bump onto all the particles in the metal, so they gain heat from the hot end and race down, bumping onto the particles on the cold end, therefore spreading heat through the metal much quicker. And this is why metals are so amazing at conducting. So you need to remember that conduction is the transfer of a heat by collision of particles. Solids are the best at conducting because the particles are so close together. Liquids would be next best, and gases are the worst because the particles are so far apart they don't collide very often. Also, metals are the best of all solids in conduction, and this is because they have free delocalized electrons which can transfer heat from one end to the other very quickly. So we have seen that of all solids, metals conduct the best. But even then, it is important to mention that some metals are better conductors than others. And you can tell that by taking rods made of different metals but being the same in length and thickness. The rods go through the stopper into a water trough at the back. Then we add some hot water to the trough, and the heat will travel along the rods towards the ball bearings. And when the wax melts, the ball bearings are gonna fall off. The sooner the ball bearing falls, the better they conduct. So we add the water and start the stopwatch, and we wait. Copper falls off fast. And then aluminium falls. Brass is next. Steel follows. and obviously zinc is the last. So you can say that the order of conductivity starting from the best is copper, aluminium, brass, steel, and zinc is the poorest conductor of the 5 metals. Another factor that affects conductivity is the temperature difference. In the just completed experiment, if we had used a direct flame instead of the water bath, the wax would have melted much faster. And this is because the temperature difference between the flame and the metal rod is much higher compared to the temperature difference between the hot water and the rods. Other factors which affect conductivity include the length of the metal and the thickness. So if you were to take 2 metal rods of different length and one end placed on a flame, you realize that the colder end of the shorter metal will get heated faster compared to the colder end of the longer metal. And therefore, the shorter the metal rod, the faster the transfer of heat. Again, if you have 2 metal rods of different thicknesses, you'd realize that the thicker metal conducts faster than the thinner one. Thermal conductivity in liquids. As expected from their structural arrangements, liquids are very poor conductors of heat. If you put a piece of ice in a boiling tube and add some water, and then you clamp it, using a Bunsen flame, you heat the upper part of the tube. You notice that water at the top is boiling, and yet the ice at the bottom haven't even melted. And this proves that water and liquids in general are very poor conductors of heat energy. And you can imagine in gases, conduction is almost impossible. So we have looked at conduction and have seen that liquids and gases are really poor at conduction. But heat can transfer through them fairly easily, and the way that happens is by convection. Convection occurs only in fluids or simply liquids and gases, and the way convection occurs is the same in liquids and gases. So let's consider these gas particles in a room. They all have roughly the same energy, which we can see because they are all moving at the same speed. Let's pour some fire in the room. Okay. Now the particles by the fire start to gain energy from it, and they start to move faster. And because they are moving faster, they spread out. So they become less dense, and because of that, they rise. So when they rise, they can't leave nothing behind. So the cooler air or fluid moves down to replace them. Now this cooler fluid is by the fire. So these particles start to gain energy, they become less dense and they rise. And other cooler particles move down, get heated, gain energy and rise. This happens over and over, forming what we call a convection current, and that's how heat is transferred through fluids. So let us look at the convectional currents in liquids, and let's set up an experiment or some experiments to see the convection currents in water. We take a beaker of water, some potassium permanganate, and guide it to the bottom of the beaker. We then heat the beaker at one corner. The hot liquid begins to rise towards the surface. Cold liquid is drawn in to replace it. On reaching the surface, the hot liquid begins to cool. This causes it to sink and drawn in to be heated once again. This sets up a convection current, and this eventually transfers heat to the whole volume of water in the beaker. But why does this happen? Look, as the liquid is heated, the particles gain energy and move further apart. The liquid expands, becomes less dense, and starts to rise to the surface. New liquid is drawn in to replace it. Meanwhile, the hot liquid at the surface begins to cool. The particles get closer together, or the liquid contracts, becomes more dense, and sinks. A convection current is set up, and the process is repeated over and over again. Another way of demonstrating convection current is using a convection tube. This is a rectangular tube with a mouth at the top. We fill it with water and heat it at one bottom corner. Potassium permanganate crystals are introduced at the mouth. Notice that the colored water is moving in an anti-clockwise direction. Can you explain why that is happening? You see, when the water is heated, a convection current is set up such that water near the flame gains heat, it expands, becomes less dense, and rises vertically along the right arm. Cooler water along the lower horizontal section is drawn in to replace the rising water. It's heated, and that too rises. This process continues, setting up a convection current in an anti-clockwise direction. Of course, as you can imagine, if we move the candle to the other end, the convection current is reversed. It goes clockwise. Just like in liquids, gas molecules when heated gain energy, they expand, becomes less dense, and they rise up. Less dense molecules sink to take up the space and are also heated, expands, becomes less dense, and they rise. A convection current is therefore set up just the same way as in liquids. For instance, in this demonstration, we will use a smoke chamber which contains a candle as a heat source and two chimneys, one of which is above the candle. First, we light the candle to heat the air above it, and then we close the screen. If we have some smoke above the candle, the convection current forces the smoke upwards. However, if we do the same above the other chimney, the smoke is drawn down into the smoke chamber. So you see, in the convection current, warm air moves upwards and cold air is drawn down the other chimney, dragging the smoke along. Now, take a look at this experiment and try and explain what is happening. Why are the tea bags rising? You see, it's all about the convection current being set up by the air molecules. When the tea bags are burning, the air near them is heated. It expands and becomes less dense and therefore rises, along with it the less weight tea bags. And convection is responsible for the powerful currents in the oceans. These are dangerous for swimmers and drives the Earth's climate. There is also huge convection currents in the magma underneath the Earth's crust. These are responsible for the movement of the Earth's tectonic plates, which lead to earthquakes of volcanoes. Which reminds me that lava lamps use convection too. Look at the hot wax blobs rise as it becomes less dense. And while Earth makes use of convection, birds use thermal upthrust of hot, less dense air. That allows them to glide effortlessly as they search for food. Wind itself is also caused by convection, from a gentle summer breeze to a hurricane. Land and sea breezes are also caused by convection. During the day, the land heats much quicker than the water. Therefore, the land is hot and the water is cold. The hot air above the land becomes less dense and rises. This means that cold, less dense air from the chilly sea is drawn in to take its place. It is this cold moving air that we feel as sea breeze as it moves from the sea to the land. But as the day turns into night, something strange happens. The situation changes. The land cools down much faster than the sea. Okay? So the sea is now hotter than the land. So the hot air is rising above the sea as the cold air is drawn from the land towards the sea. So the wind direction has been reversed. Next we look at heat radiation. So we have looked at conduction and convection, and both of them require particles to transfer heat. But heat manages to reach us from the sun, and there's definitely no particles in space. It is a vacuum. What about the atmospheric gases, you might ask? Remember, the atmosphere is not an infinite layer extending up to the sun. No, it only extends a few kilometers above the Earth's surface. Then again, even if the gases were to transfer any heat, convection currents would be set up moving upwards and not downwards to the Earth's surface. So then, how does heat from the sun reach us? It travels as radiation, infrared radiations or heat radiation to be precise. So let's look more into radiation, and we actually find that different colors are better at emitting heat than others. All hot objects emit heat radiation, and this is the physicist term of hot. What it essentially means is that any object above 0 Kelvin or minus 273 degrees Celsius. That's what physicists mean by hot. So anything above this will emit heat. However, it will also be absorbing heat radiation, and it is only if it is hotter than the surrounding that it is actually going to be emitting heat overall. Let us add boiling water to this cube to make it hotter than the surrounding and see what happens. First, let's look at the shiny silvery surface, and you see it's really poor at emitting radiation. Then we move to the white shiny side. That looks better, but still it's poor in emitting radiation. The matte white side, it's slightly better, but still not so good. When we go to the black shiny surface, and you see it's emitting a fair amount of radiation. Now let's see the matte black side. Now that looks excellent in emitting heat radiation. So matte black is the best color at emitting heat radiation. Then what colors are best at absorbing heat radiation? We've seen that matte black is the best at emitting heat radiation. Let's see. We have a heating source that is a fire. We're going to stick using wax 2 marbles on 2 couples of plates. One plate has a shiny surface and one with a matte black surface. So whichever surface absorbs the most heat radiation is going to melt the wax the fastest, and therefore the marble will drop quickest. Let's wait and see. First, acknowledge that the shiny surface is reflecting away all of the radiation. The matte black is absorbing all the radiation. So there we go. The matte black fell off way in advance. The shiny silvery surface is still stuck on there. It is because the matte black surface is absorbing all that radiation. Shiny surface is reflecting it all. So then, when heat is transferred across a vacuum, The only way it can do that is by radiation. We've also seen that matte black is the best absorber and emitter of radiation. So if you want something to heat up really quickly or something to cool down quickly, we color it matte black. We also saw that the shiny silver is the worst in absorbing and emitting radiation. So if you want something to stay hot or something to remain cold, you color it shiny silver. If you have two tins of equal size, one colored black and the other is shiny silver, fill them with water and place them in the sun. Then take the temperature of the water after some time. You can already guess which water will be hotter. The black, of course, because the black absorbs heat radiation while the shiny silvery surface reflects much of the heat. And so it is not surprising that houses in hot areas are painted with shiny colors to reflect away as much heat as possible. In solar concentrators, electromagnetic waves in the form of radiant heat are reflected to a common point or focus by a concave reflector. The temperature at this point can be sufficiently high to even burn very hard objects. In a solar heater, a reservoir kept at a higher level stores water. It is connected to a small cylindrical tank kept at a slightly higher level above the heater. One end of the copper pipe is connected to the bottom of the small tank, with the other end connected near its middle. Water from the tank flows continuously through the pipe, and the water absorbs heat as it flows through the solar heater. Hot water remains at the upper portion of the tank, and this can be drawn through a pipe, and water from the reservoir tank flows to replace the hot water drawn. Next is a vacuum flask. Now, a vacuum flask or the thermos flask is designed to keep hot things hot and cold things cold. So vacuum flasks are designed to reduce heat transfer. The vacuum flask is designed to reduce heat loss via conduction, convection, radiation, and evaporation. Now, this is the graphic representation of a vacuum flask. We have a plastic top, silvered glass walls, a vacuum between the glass walls, and plastic supports. We shall see how each of these reduce heat transfer. The plastic top first. This reduces energy transfer by conduction, convection, and evaporation. First of all, plastic is a good insulator, so it reduces conduction. Heat transfer by convection is reduced since convection currents are blocked by the top. And heat transfer by evaporation is reduced as water molecules which evaporate are trapped inside the flask. Now, the silvered glass walls. And this reduces heat transfer by conduction and radiation. Glass is a poor conductor, so that reduces heat transfer by conduction. Silver reflects infrared radiation back into the liquid and stops it being emitted. Between the layers of the vacuum, this prevents both conduction and convection, and that's because both of these require particles. In a vacuum, there are very few particles, and thus reduces both conduction and convection. Finally, the plastic supports. This reduces heat transfer by conduction. As we've seen, plastic is a good insulator, so conduction of heat is reduced. And so the ability of matter to transfer heat from a hot to a cold object is called its thermal conductivity. and it's based on the structure of that material both at the atomic and molecular level. So if you have something like a metal, which is a good conductor of electricity, then it's probably also a good thermoconductor. And the reason why is that there are these delocalized electrons which allow heat to move through the metal. Now, nonmetals can pass on heat, just not as well.
When thinking about your career and wondering what to study to equip yourself for the working world, MSc is the college to help you make this decision. We have 23 campuses nationwide and a wide range of aligned and accredited programs to choose from. Best of all, easy payment terms and flexible class times. MSc College is your ticket to a better life. Call 0860 672 265 or visit msccollege.co.za.